given data that we got a cylindrical block. So we got a beaker, and inside our beaker is a cylindrical block of ice which is at minus 25 degrees centigrade, and inside the block we have placed a heaters. Okay, so this heater is connected to a power supply which is transferring energy at 50 joule per second. Okay, so the rate of energy transfer, and we got the specific heat capacity and everything that we need to integrate. So that will be what amount of energy absorbed by this ice to raise its temperature from minus 25 degrees centigrade to 0 degrees centigrade. And ice, we also got the mass of ice and specific heat capacity. Okay, so it's pretty easy. Q is equal to mc del theta, and change in temperature is 0 minus 25, that is plus 25. Q is equal to m 92, that is 92 times 10 to the power of minus 23. All right, and then we got C, which is 2110 joule per kilogram per Kelvin, and we got change in temperature which is 25. So Q will become equal to, we just need to multiply these terms. Sorry, not 23, sorry, 10 to the power minus 3, because it's gram to kilogram is 1 gram is 10 to the power minus 3. Okay, 4.853 times 10 to the power 3. 4.853 times 10 to the power 3 joule. So that's the energy absorbed. Okay, in second part, now that we have reached 0 degree centigrade, ice will start converting into water at 0 degree centigrade. So in the second part, he is asking us that calculate the energy needed to melt all the ice once it reaches 0 degree centigrade. Calculate the energy needed to convert ice from water, convert ice to water at 0 degree centigrade. So we are going to, let me just call it Q1. That's our first type of energy that is being transferred for absorbing. That's the energy absorbed by ice to raise its temperature. And now we are finding another type of heat energy, Q2, that will be used to convert a state of matter, and it is equal to mL, where L is the latent heat of fusion, which is given here, that is 3.3 times 10 to the power 5. So we again do 92 times 10 to the power minus 3, and latent heat of fusion is now 3.3 times 10 to the power 5, and when we multiply these two terms, so we get times 10 to the power 4 joule. Okay, so we got the energy that is needed to convert ice from ice to water. Okay, so these two values are really important for our next part, Q2 and Q1. So we write them here. Q1 is equal to 4.853 times 10 to the power 3, and Q2 is equal to 3.036 times 10 to the power 4 joule. Okay, because for our next part what we need to find is how much time will it take from minus 25 degree centigrade to 0 degree centigrade, and then at 0 degree centigrade the conversion of ice to water. Okay, so the third part that we need to find, so from minus 25 degree centigrade to 0 degree centigrade, what we need to find is total energy first. So total energy E total is equal to Q1 plus Q2, and Q1 is 4.85 3 times 10 to the power 3 plus 3.03 times 10 to the power 4, and if we add these two terms, what we get is total energy is 3.513 times 10 to the power 4 joule. Okay, so if you move 0.1 digit here, it will be 0.4853 times 10 to the power 4 plus 3.03 times 10 to the power 4. You can take 10 to the power 4 common, and then 3.03 plus 0.48, this will be 3.52. Okay, so this gives us this amount of total energy. Now that we know the total energy, so the time taken is equal to total energy divided by rate of energy. Total energy divided by rate of energy. So the rate of energy is given here, which is 50 joule per second. So total energy is 3.5213 times 10 to the power 4 and divided by 50. So the total time will be, if you divide these terms, you get 704.26 seconds. Okay, the total time taken. Joule will cancel out. This is per second. It will go on the top, and we get like joule divided by joule per second, joule multiplied by second per joule, and we got the unit second with it. Okay, he says assume that the temperature, room temperature was 25 degrees centigrade. Okay, and the beaker that we are using has an insulation on it. So if the beaker has insulation on it, and we are taking our experiment at 25 degrees centigrade, what will happen? How will it affect our temperature, our rate of conversion? So if we have insulation, we already know that heat from hotter body moves toward colder body. So the tendency in the heat is it moves from hotter body to hotter substance to colder substance. But now that the temperature, the beaker has been insulated, so it will slow down the conversion process, because no heat from surrounding can reach the beaker. So when we have placed an insulation on the top of it, the hotter body on it, it will slow down. So the short answer that for 1 mark would be that if the beaker is insulated, the rate of conversion of ice to water will slow down. And then if you want to explain it, how will you explain it? That because the room is at higher temperature, the beaker is at lower, the heat from room is trying to move toward the beaker, but because there is an insulating layer, there is a thermal insulation, it cannot move. So that's why the conversion will be really slow.